This is the Lecture 12 Q&A. I actually forgot to start the recording at the beginning of the Q&A, so I missed a few questions. I'm just going to answer them quickly right now and then go into the recording for the actual Q&A session. One question was, can a tree have any number of branches, more than 2? The answer is yes. A tree can have as many branches as you want. A tree where any node has at most 2 branches is called a binary tree, and that's quite important for efficient algorithms that you'll talk about in 61B. But for representing stuff in the world, trees with an arbitrary number of branches are quite a bit more common. So that's what we'll focus on in this course. A second question was about the optional second argument in the built-in sum function. Why is it the case that you need that at all? Well, when you sum 3, 4, 5, what you're really computing is the result of adding 0 to 3 to 4 to 5. And why is this the case? Well, if you sum an empty list, you get 0. So built into sum is this notion that you're starting with 0 and then you're adding other arguments in. So what about adding something besides numbers, like lists? You can add 3, 4, 5 together, but if you take these two things, 3 and the list 4, 5, and put them into a list and call sum on that, you get an error, unsupported operand type plus for int and list. Why is that? Well, Python tries to process this the same way that it processed this, which is to add 0 to the list 3 to the list 4, 5. That gives you this same error. And the error comes from adding a number to a list. Python doesn't know how to do that. I don't know either. What you'd really like to do is start with a different notion of 0. The most 0-like thing in the world of lists is the empty list. If I added an empty list to the list 3 and the list 4 or 5, then I would get the same result as if I hadn't had the empty list there at all. And you can get the built-in sum function to do this by saying, here are the lists that I want to sum together or add together, but the 0 that I want to start with is the empty list. The next question was about trees. Here's our tree data abstraction from lecture. And in particular, a student asked, what happens if you ask for the branches of a leaf? A leaf is a tree with no branches. There still is a list of branches. It just happens to be that that list is empty. If I actually loaded this file, then it would be easier to see what I mean. Okay, so a leaf is a tree that has no branches. You can still call branches on it. You just get an empty list. That's what I mean by no branches, is that there is a list of branches. It's just empty. And you can see why that's happening. The representation that we've chosen for a leaf is just a list that contains the label and nothing else. And so if I were to call branches on that, I would be evaluating this expression, which gets all of the values in this list, which has only one element, starting at element number 1. But there is no element number 1, and so you end up with an empty list. If I were to write for b in the branches of this leaf, since branches leaf returns an empty list, b will never be bound. If I were going to do something for every branch, since there are no branches, hello never gets printed, and b is not bound to anything. Okay, I think that's most of the questions that we covered before I remembered to start the recording. So from here, let's see what happened in the actual Q&A session. Okay, so this question was about tree processing, which is confusing, and whether we could do an example that doesn't involve like labels and branches. And I think the answer is no. These could be named differently. Like instead of calling it a label, we could call it something that had more meaning for the application that we're building. So if we were representing the course website, maybe the label would be the address. Like there's a address for homework, and there's address for the main calendar. And you could think of one branch of this tree rooted at the whole thing as anything that you can get to by following a link. So there's like we followed one branch, and now we're at a new label. But I think that might change the word label to be address and branches to be list of other pages, but it wouldn't change the implementation at all. And so it really is worth getting used to the idea that this concept of having a label and then a list of branches, which are trees, is true of any hierarchical representation that you care about. So anything you want to model is often built up out of a label and some branches. And if it's ever the case that the pieces of something are the same kind of thing as the whole thing, so like the pages that are linked to from a page are just more web pages, then you get this kind of tree structure. I'm guessing that's not so helpful.
Let me offer one more thing. A slightly more general version of a tree is what's called a graph, which we won't be talking about. And there we often talk about nodes or vertices and edges. So edges connect two things. And the vertices or the nodes have the name of something or with a value associated with it. So think, for example, airports around the world, every airport is a node and an edge connects them if you can fly from point A to point B. Now, that's not quite what a tree is, because a tree has sort of this ancestral relationship, top to bottom, whereas a graph typically doesn't have that notion of hierarchy. So that's why I think the branch nomenclature here is good, because it reminds you of this sort of upside down tree.
All right, interesting. So the question is about this optional lab question, which involves coming up with what letters you need to add to W1 in order to get to W2, assuming that W1 is a subsequence of W2. So W1 might be cat, W2 might be contrast, and this is supposed to return the ONTRS that you need to add to cat in order to get contrast. So maybe let's talk about this for a moment and how you might go about it. You have a choice of whether to work through the words from the beginning or the end. And there's some condition here that says, like, when there's repeated stuff, it should happen in a particular order. I think we can just ignore that for now and focus on getting some reasonable answer, and then we could worry about this kind of condition. And therefore, I don't think it matters whether you work through the words from beginning or from the end. But the way I would approach this problem is to say, these two words, assuming they're not empty, have a first letter. And that first letter is either the same or it's not. If you know that all the letters in W1 are somewhere in W2, then if the first letter of W2 isn't the same as W1, it's one of those letters that you're going to have to add in order to transform W1 into W2. So that's kind of the key check, is that you want to keep around the first letter of W2 if it's not the same as W1. If it is the same, then it's not something you need to keep track of, because our goal is to find everything that's in W2 but not in W1. And if we find a letter that's in both, well, then I think we can just leave it out of the final result. So no trees needed. How might we go about this? Well, we'll leave the base case till later. So I think we can work it out pretty soon. And just say, like, oh, let's assume that W1 and W2 both have letters in them. If W1's first letter is the same as W2's first letter, then I kind of just don't care about it. It's not supposed to be part of the result. So I can just find all the letters in the rest of W1 and the rest of W2. I've kind of just like worked my way past that first letter. And I don't want to include it in the result. I think if, on the other hand, if these letters are different, then we actually do need to have W2 0 as part of the eventual response of letters that we want to add. We don't want it twice, so I think it's fine to only process the rest of W2 after that. But we still haven't matched up the first letter of W1 with anything, and it's supposed to be in W2 somewhere. So I don't think we want to change W1. Instead, we'll just keep it the way that it is. All right, Here we made an assumption that they both have letters, but I guess there's a case where we might have used up all the letters in W1. So I think we need to worry about that. One way to write it is that. Let's leave it like that. That's fine. Then what are all the letters that you'd have to add to an empty string in order to get W2? I think you'd have to add all the letters in W2 to get that.
Mm-hmm.
So let's see how we did. And then we will discuss how to fix it, because there might be a weird condition with this cacophony case that we'll have to worry about. Oh, maybe we just got them all. Okay, yeah, so I think if we had like worked from beginning to end, from the end to the beginning, then this condition where like the order matters might have come out a different way, but turns out we didn't have to worry about that.
By the way, this is sort of a classic recursion problem where you can see, if you think about the problem as well, what if I have just there's one letter in each and those match? What do I do? Right? And then what do you do otherwise? It's that classic recursion where you sort of simplify the problem to the simplest possible cases. The base case, one of them is empty. And then here, there's sort of like two base cases almost. Not quite, because that second one is a recursion, but it's that really, really simple case. And then you build in the complexity after that. So that's what's sort of really cool about these recursive solutions.
Yeah, good question. So I think part of the question is about what guarantees do you have with the tree data abstraction? Like, how do all the pieces fit together? There's actually a lot of them, so let's just talk about them all. When you call label on something, it should always be the result of calling tree. So it should never be the case that you call label on anything except for something that was created by calling tree. Same with branches. Whenever you call branches, it should be on something that's a tree. What does it mean to be a tree? It means it was the return value of a call to tree. This is not specific to trees. This is true of selectors and constructors in data abstraction in general, is that all your selectors should take only the result of calling their constructor. The constructor for a tree cannot take arbitrary values. For the label, it can. A label could be anything. But branches needs to be a list, and it needs to be a list of trees. It could be empty, but if it has anything in it, it's not allowed to have numbers in it or strings in it. It has to have trees in it. What does that mean? It has to have values that were the result of calling the tree constructor. So when you call tree on anything, you can put whatever you want there. But here, you have to put calls to tree. Now, it doesn't always look like this. Sometimes you're calling some other function which returns a call to tree. So that would be okay if the definition of f was return a tree, return tree of something. But this value that ends up in here needs to be a tree. And that is the recursive definition of this particular data abstraction, which shows up in computer science all the time. So we're spending a lot of time on it because it is very useful in general.
And by the way, notice there's a very good reason for this. This isn't arbitrary. Look at the code, for example, is tree. It's assuming that everything as you process down has to be a tree. So that assertion up top ensures that the functions that operate on trees have a data structure that's intact.
And what's so great about this is that when you do something like count the leaves or whatever, and you are sure that what got passed in was a tree, then you know that, if it's a leaf, there's just one leaf, right? There's nothing else there except for the leaf. But the useful part is that if it's not a leaf, then you can go through all the branches and you know that every bee is also a tree, which means you could call count leaves on it because count leaves takes trees. You could call any other function you want that takes trees, and you have this guarantee that all of the b's that you get when you iterate through the branches of a tree are also trees, and therefore you can do things with them that you can do to trees. So we could, sum up the leaves in each branch, or something like that. Now, building a tree always takes a little bit of work. You got to set up the label, and you got to set up the branches, and those branches need to be trees. This branch has only one tree. This tree has only one branch, which is a tree, so that's good. It's a leaf. And therefore, if we count the leaves as that, we should find only one. Maybe I didn't save. Oh, wrong file. Oh, and I need to return. We're getting close, folks. Okay, one leaf. If I added another leaf, regardless of its label, we'd have two leaves. I don't know if that answered your question, so maybe I'll let you respond. So branches always returns a list. If that list is not empty, every element is a tree, but it might be an empty list. So you don't know when you call branches whether you're going to get no branches or 2 branches or 1 branch or 50 branches. All you really know is that you're going to get a list, and that list, however many elements it has in it, are all going to be trees, meaning they were all created by calling this tree constructor. So the question was about this kind of just for fun question, anonymous factorial. I'd say that it's outside the scope of this course, that you'd be able to work this out on your own. But it's a fun thing that you can do. So the goal here is to figure out how to get recursion to happen, meaning write a recursive function without being able to assign a name to that function. In this example, we wrote a recursive version of fact, but we referred to fact by assigning it a name. And the trick to avoiding assignment statement here is the same one that we saw in ping pong, which is that instead of using an assignment statement, just pass in something as an argument, because that's another way to give something a name, is to pass it into a function, and then it has a name. So if we have this general structure, here's a function that takes a number. If n is 1, then it returns 1. Otherwise, it multiplies n by the factorial of n minus 1. And maybe we'll get rid of all these moles and just make our life easier. Nothing wrong with subtracting like that. How would we give this thing a different name? Well, instead of assigning, we could have it be fact. But then how would we pass that in? I guess instead of putting it here, maybe the best place to put it is here. So basically, in order to run this, we need n and we need factorial. I'll just let that sink in. If factorial is not already defined, then somebody needs to pass it in order for us to call it. I'm going to need a little bit more space than this, I'm afraid. Now that we have a function that takes n and factorial, we need to be a little bit careful. We want this to be our factorial function, but it takes 2 arguments. And here we're calling it with only 1 argument. So that seems like a mismatch. What should be the second argument every time we call fact? Well, it should be the same function again. That's kind of how we get that recursive structure, is that every time we call this thing that takes in a number and the function that we're going to call recursively, it needs to be called on a new number and the function that we're going to call recursively. So we've actually made some progress, even though all we've done is kind of move a name in here and pass it around. The last part is that we need to figure out how to write a function that takes only n. and somehow calls this one instead. And that's actually not so bad. This says, give me a function and call that function on both n and itself. So if I have a function and I call it on n and itself, where n comes from here, now I just need to know which function I'm supposed to be calling on n and itself. And the answer is this guy. So let's see what g does now. G computes n factorial. If we really wanted to get rid of that assignment statement, then we could compute 4 factorial this way by taking this function and calling it on 4. And then, hopefully, if everything went right, we will have printed 4 factorial or 5 factorial or whatever. So, what was the key moments in figuring this out? One was, if we can't have fact defined already, then we have to pass it in as an argument. And the second was, if we have a function that takes 2 arguments, and we really want a function that takes 1 argument, then we should write a function that takes 1 argument and calls the function that takes 2 arguments. And then the last part really is kind of a trick, which is to say, like, if you had a function and an argument, you would then call the function on the argument and itself. This is basically how you create recursion without using assignment statements, is this little part right here.
Man, that's gnarly.
Remember, folks, just for fun.
John has a very odd sense of humor, apparently.
Odd sense of fun, that's for sure.
Odd sense of fun. I think John's right here, by the way. Look, there's a couple of things that you've seen before. Essentially, there's the helper function in here. You have a function that only takes 1 parameter n. You really need to pass 2, so you put a helper function in. That's basically what you have here with the lambda. You've got sort of the notion of recursion, and then there's just that little trick there, which you see with this lambda f of n f. So don't get too worried if you didn't see that obvious. I don't think it's at all obvious, actually.
One thing that's exciting about this, while it's not obvious at all, is that it allows you to create iteration out of just functions. Like, of course, there's no assignment here. There's also no while statement or for statement here. But we are doing something repetitively. And so this is kind of, this idea right here is a building block for the claim that once you can define functions, you can kind of write any program that you want. You can perform any computation. And you might wonder, well, is that really true? Like, don't I need a while statement or a for statement? It turns out technically you don't. That does not mean we should get rid of while statements and for statements. They're a lot more readable than this, I think. But they're not strictly necessary in order to perform interesting computations.
Yes, and somebody in the chat just pointed out Scheme and Lisp this is sort of the premise of these functional programming languages that don't have explicit looping constructs, as you do everything with these types of constructs. And it's a little bit mind-bending, but it turns out it's expressive enough.
Yeah, that's right. Those languages do tend to have assignment statements, so at least you could write this instead of instead of that.
Yeah, and to the chat room, we do still need conditionals.
The next question was, what was the purpose of the fact times example from lecture? Yeah, so the reason we did something a little bit different here was so that we could show an example of a recursive function that just called itself without doing anything with it. So there kind of wasn't anything outside of the call. Everything happened inside the call, where we subtracted 1 from n, and we multiplied k by n. But we didn't like add anything or multiply anything afterwards, which was different than the original version of factorial, which did multiply the result of the recursive call by n. The original one looked like this, right? It was like if n equals 0, return 1, else return n times fact n minus 1. So here we make the recursive call and then we like do some work afterwards. And that means the recursive call doesn't really know where it came from. It doesn't know anything about which factorial result you're constructing. Whereas this one does. At the end, when you hit the base case, you have computed k times n factorial for whatever n in k you started with. And that is now named k, which is a little confusing, but that's how it goes sometimes with recursion. But the point is that the whole answer is built up by the time you hit the base case, at which point you just have to return, all the work is done.
And notice, by the way, in that first one, that's not true. As you're doing recursion, there is a delayed gratification of the evaluation of that product. So when you hit the base case in the first fact, you then have to go back and now multiply all those numbers between n and 1. Yeah, because you built an expression, whereas in the fact times, you basically have an assignment operator. It's that you're just using the parameters as the assignment operator. And so when you hit that base case, done, I've got the answer. So you're right. Of course, we could have done it differently. We didn't have to do it this way. But you see that structurally, the recursion is subtly different here. And it turns out this has a real implication too, by the way, downstream. And I think we'll eventually do that, right, John?
Yeah, so this is called tail recursion, and this is not. And we'll talk about this later when we talk about interpreters. So the goal here wasn't to implement fact times. It was actually to re-implement fact. But in order to re-implement fact, you'd have to have a helper function. That's what fact times is. That keeps track of 2 arguments instead of 1. The thing you're trying to compute the factorial of, and the result, the answer of computing n factorial.